Okay, now I think we're on business. How's everybody doing? Doing okay? Yeah. Okay. Good. So since Friday, I put those two homework assignments in there. So the first one, which is the stuff from second quantization, we've covered all that material, and then I don't remember the second one if we've covered everything yet, but we will today. So this will give you all the background you need to solve those problems. And like I said, the last one's not that hard. Um, if you've been paying attention just a little bit. But if you have questions about anything, always let me know. So last time we started to move into the realm of relativistic quantum mechanics. And before I do that. So, and then I also said that the final exam is a week from this Friday, right? Is that the last day of class? Not this Friday, but yeah, a week from this coming Friday. So about a week and a half away. Yeah. Okay. And there won't be class on Wednesday. There's a kind of a teleconference that I have to go to. So I'm available on Wednesday. So the next time we'll meet will be on Friday. Okay. I'll send out an email for the people that aren't here. Okay. So we started last time talking about kind of the marriage of quantum mechanics and special relativity. And we saw that, it's kind of a rocky marriage between the two. So at the beginning of the 20th century, we had these two really successful theories. One was quantum mechanics, one was special relativity. And so people tried to, merge those two to try to develop a theory for, fast-moving small particles, basically, right? And so to do that, we have to make sure that we obey all the rules, right, of special relativity and quantum mechanics. Special relativity tells us that the most important thing is that we have to put space and time on an equal footing, right? So we treat them in the same way. And what we saw from when we first wrote down the Schrodinger equation, we already saw that we're breaking that rule, right, explicitly. So we're if we just blindly apply relativistic mechanics to quantum, to a quantum system, we see that the time dependence is linear, or on the right-hand side, the spatial dependence is quadratic, but it's under the square root, and you don't know how to really deal with these square roots when you're talking about operators. And so we said, well, you could Taylor expand, right? And that way you'd have del squared outside of a square root. But the problem is there you have to include all terms in that series, and so the theory becomes very non-local, right? So you're breaking causality, right? So we kind of put that that question to the side for a minute, and we said, okay, well let's do this. Let's, instead of working with the Hamiltonian, let's work with the Hamiltonian squared, because then we can get rid of that square root, right? And so, but basically what we do is, use this relationship for operators that commute and iterate over the Schrodinger equation. In other words, we apply the operators on each side twice, right? So we get the Hamiltonian squared, and over here we get the time derivative squared. Oops. Oh. Right. And so we said, okay, now we're at the same order, right? And so we went through. We could pretty it up a little bit using relativistic notation, and you can combine the time and the spatial dependence into this del squared operator, right? And this is the Klein-Gordon equation. And like I said, if you take quantum field theory, you'll see this a lot, right? Because it's kind of the starting point. It's kind of the simplest quantum field theory that you can write down. And so we wanted to ask, is this a good equation, though, for relativistic quantum mechanics? And we ended up, we saw that the Hamiltonian, when we square it, we're kind of implicitly implying that we're also allowing this minus sign to occur for the Hamiltonian. And so it looks like we're going to have negative energy solutions, which is, at the time, was not a good thing, right? We didn't really know how to interpret negative energy. But putting that aside, we looked at We wanted to see if we still, if we didn't mess up anything in quantum mechanics, right? So special relativity, we're good. In quantum mechanics, the way we check this is to basically construct the continuity equation. And what we found was that probability, the stuff, if you want to define this thing inside of these parentheses as probability density, you see that this equation is telling you that we're not conserving probability, and that's a really bad thing in quantum mechanics, right? That's kind of the basis on what we build on. And it turns out that linear time dependence is mandatory if you want to write down a quantum mechanical equation like the Schrodinger equation, because if you go any higher, it breaks the conservation of probability. So we said, okay, well, we're breaking quantum mechanics in the worst possible way, so obviously this is not a good candidate. The Klein-Gordon equation or the Klein-Gordon theory is not a good candidate to describe relativistic particles, right? So then we went and looked at the way that Dirac thought about things, and he said, well, I know I need to keep this linear, right? And so what I need is the spatial part to be also linear. And the only way that'll happen is if I can rewrite this stuff under the square root as a perfect square, right? With inside that perfect square space being, linear. And so that's what he did, right? So that's what he did. And so basically he's saying, okay, that stuff under the square root, we can write it like this as a perfect square. And as we can find alphas, 3 alphas and 1 beta that satisfy, that let us do this. So he wrote down the equation, linear in time, linear in space, and this is called the Dirac equation. I don't know if he called it the Dirac equation or if he called it the me equation, but it's called the Dirac equation. Okay, so we asked, okay, so what about this alpha and beta? What are they? And we ended up finding a whole set of rules or a whole set of constraints. Basically, they're matrices, right? They had to be matrices. They had to be traceless, and they have to have eigenvalues of plus or minus 1, right? And all that was just came from, well, a lot of it came from this, computing this thing, making sure it gave us what we wanted. And like I said, this thing's a little harder to prove. They have to be traceless and eigenvalues of plus or minus 1, but you can prove it, right? And they have to be even dimensional, right? So it sounded a lot like the Pauli matrices, right? Because the Pauli matrices are, traceless. They have eigenvalues of plus or minus 1, and they're even dimensional, right? They're 2 by 2 matrices. The problem is that we need 4 matrices for the Dirac theory, right? And Pauli matrices, these 3 guys span the space, right? So we can't add a 4th. So that meant we had to, if we wanted to keep the theory the way it is, we had to promote our spinner from a 2-component spinner to a 4-component spinner, right? Because these the matrices alpha and beta are now going to be 4 by 4, and it only makes sense that the spinner be a 4-component matrix, or 4-component vector, sorry. And then so there's several different ways writing down alpha and beta. We'll always use the vial representation, and you'll see why maybe today or next lecture why this is the best choice for us. They're 4 by 4 matrices. We have a 4-component spinner. All right. The question was, how do we interpret these extra states? And we can use the fact that the Hamiltonians built out of alpha and beta are traceless, right, and even dimensional. So that means all that stuff applies to the Hamiltonian as well. And so generally, in general, you can write down the eigenvalues. There's two positive eigenvalues and 2 negative eigenvalues, right? And these 2 extra states are what we call negative energy states. We said, well, we'll come back to that. Let's just forget about that for the time being. And then finally, we ended up by proving that this thing does conserve probability, okay? The Dirac equation, right? So we constructed the continuity equation and saw that, sure enough, it predicts, as long as you identified psi dagger psi with a probability density, this thing conserves probability, the Dirac equation. So we're good. So now we know that we're good in special relativity because explicitly we have time and space on the same footing. And now we've just shown that quantum mechanics, we haven't broken quantum mechanics, at least yet. Okay. All right. So that's where we stopped. Okay. And so now what I want to do is, before we go any further, develop kind of a more rigorous formalism than what we've done. I want to check the non-relativistic limit. All right, so I want to take the non-relativistic limit of the Dirac equation, or some form of the Dirac equation, and make sure it gives me back what I know quantum mechanics would predict. Okay, and so what we're going to do is we're going to consider a particle that's so it's a free particle at rest. Okay, and we can do this because in special relativity that if you solve it in one frame and you apply Lorentz transformation, that it'll apply in all frames, right? So we start with the simplest frame, which is the particle at rest, okay, or the particle's rest frame, if you want, right? And in that case, the Dirac equation just boils down to this, right? Because the momentum term is 0, right? And beta has this form. Remember, it's a diagonal. And so just by, you plug in that beta, and just by inspection, you can basically solve this thing. And you get 4 solutions, right, which is what we expected. You get 2 guys, psi 1 and psi 2. Notice where their non-zero components are. So the upper parts are the positive energy solutions, right? So these 2 guys. But we also get the negative energy solution. So one where it has a component here and a component here, right? But you can see the difference in the signs of these exponents is telling us this is the positive energy solution, this is negative energy solution. Okay. All right. So again, let's forget about these negative energy solutions for the time being, and we'll come back to them at a later date or time. Okay. So what we want to do is show that these guys have kind of a sensible non-relativistic form, right? In other words, when we take the limit, the non-relativistic limit, we want to see these guys reduce to a 2-component Pauli spinor, right? Because we know that at low energies, at low speeds, 2-component formalism works great. Yeah.
What are the 2 positive solutions corresponding to the up and down spin states?
Yes. Yeah.
So if we had a particle with a larger spin, like spin 1, or whatever other one, would we have to expand our matrices to be 6 by 6?
No. Well, the problem, the Dirac spinor is, the Dirac equation is particular to spin 1/2 particles.
Oh, okay.
Yeah. So you have to handle integer spin particles a little differently. Yeah. So these are our spinners, right? So what we're trying to do is take the limit, and what we want to see is these 4 components spinners. These 2 guys kind of reduce to 2-component spinners, or Pauli spinners, if you want to call them that. Okay, and so the way we're going to do that is kind of a roundabout way, but it's the easiest way to show this. And this is where we take our particle, right? It's a particle that obeys the Dirac equation, where we're going to couple it to an external electromagnetic field. Okay, and so the way we do this is we write down a 4 potential, right? So hopefully you've seen this in E&M, but you basically combine the electrostatic potential and the vector potential into a 4 vector, right? And we call it A mu. And the easiest way to couple a particle to this potential is to just use a gauge invariant substitution, where you take everywhere in your equation where you have P mu, you take it to be P mu minus 0 C A mu. Okay? And this is guaranteed to be gauge invariant. In other words, it's not going to screw up your Lorentz invariance. Okay? And this little trick is called minimal coupling. And you should have seen it in E&M, but it's a nice little way to introduce these couplings to external EM fields. So what we're going to do is take the Dirac equation, and we just replace where we had P with P, this stuff, right? And what I've done is I've dotted out So what have I done here? So our equation looks like, go back and make sure I understand. Okay. Yeah, so I've plugged in, so so this would be C alpha dot P, right? And so the alphas, what am I trying to do? Make sure I get. So, okay, so I'm taking alpha dot P, so this is the 3 part of it, right? This would be the 0 part of the momentum 4 vector, and this is the 0 part of the vector potential, right? Or the 4 potential. Okay, so all I've done is basically just replace P with P here. P minus this stuff. Okay, and what we want to do is we want to take the non-relativistic limit of this equation, right? And so to do that, it's a lot simpler to do it in the Weyl representation. So this is one of the reasons that we choose this particular representation. And so we know what the alphas and the betas look like, right? They take that nice block diagonal form, right? And that makes sense because if we want this thing to reduce to a 2-component spinner, it makes sense that we have that there are 4x4 matrices made out of blocks of 2x2 matrices, okay? You'll see how it works, okay? So what we want to do is we're going to use the Weyl representation, and we're going to rewrite our Dirac spinner in terms of two-component, what are called Weyl spinners, okay? So this is psi, and these guys are 2-component spinners, all right? So this guy will have a spin up, spin down state, and then this guy will as well, okay? And so what I do is, so what I do is I plug in that expression, right? And I'm going to take the derivatives, okay? And let me remind myself. Okay, so these are, here, yeah, sorry. Okay, so I take this guy. It's Monday. I'm sorry. So we take this guy and we plug it into our Dirac equation, and then write our Dirac equation in a matrix form. Okay, so this is sigma being dotted into alpha, right? Or I mean alpha being dotted into the momentum piece. So I've introduced this kind of shorthand notation, right? Pi here is the momentum. It's the shifted momentum. Okay. And so all I've done is plug this expression in and written everything in terms of the matrices. Remember, these are block diagonals, so this guy's actually a 2x2, right, with MC squared on the diagonals. And then I can multiply, I can do the matrix multiplication and end up with an equation that looks like that, okay? So I haven't done anything special yet. All I've really done is kind of decomposed or rewritten the Dirac spinner in terms of these two-component spinners. Okay. All right. So now we're ready to take the non-relativistic limit. Okay. And when you do that, when you take the non-relativistic limit, this thing's going to go to 0. It's going to get really small, right? This guy is small already because of this electromagnetic coupling, right? And so what's going to happen is that the rest mass term is going to dominate. Okay. So in the non-relativistic limit, the rest mass term dominates. First 2 terms are negligible. And then our time dependence of the Weyl spinners is basically pretty trivial because now all I have is this thing on the left-hand side equals this thing on the right-hand side, right? And that's just a simple differential equation that you've solved probably 1,000,000 times in your life, right? And the time dependence looks something like this, okay? So what we're doing is basically, phi and chi implicitly depend on time, right? Obviously, because I have this time derivative here. Okay, but what I'm doing by taking this approximation is saying, okay, these guys which depend on time look like these guys times this piece, right? So this is kind of our time evolution operator, right? And we're going to assume that these guys, they might have a little bit of time dependence, but they're very slowly varying, right? So most of the time dependence is coming from the rest mass piece. Make sense? Okay. All right. So what I want to do is take this guy, which is our approximate spinners in the non-relativistic limit and plug it back into this guy, right? And so what I get when I do that, and I take some time derivatives, and then I cancel off all the common factors, is something that looks like this. Okay, and so you can see that some of these terms don't change, but you get this 0 here because of the time derivative. There's the time derivative get over here, and it cancels that piece. Okay, so if you go back and look, you see that chi twiddle here is gone. Okay, and I encourage you to work through this. Okay, make sure that I didn't make any mistakes. All right. And so what we're considering is the non-relativistic limit. So we want to consider small kinetic energies, and like I said, the interaction terms are going to be small anyways, compared to the rest mass, right? And so if that's the case, these guys are going to be small. And if I look at the second equation, in other words, the equation for chi, I can solve this equation, right? Because I have, remember that, what am I trying to say? So these guys have a very small time dependence. Okay, so this derivative is going to be small. Right? It's going to be almost 0. So we can neglect this guy and this guy, right? Oops. And so what we find is we can solve the second equation. In other words, this lower component, and get an approximate solution for chi in terms of phi, right? And because we're in the non-relativistic limit, where this guy, this is the momentum, is much smaller than the rest mass, this thing, chi, we can think of as being the small piece, right? The small piece of our 4-component spinner, right? So remember, we're writing the Dirac spinner in terms of these two-component spinners. And what I see is that chi is small, right, in the non-relativistic limit, so it's kind of decoupling. Right? It's decoupling, meaning it's we can neglect it, right? And the important part of the spinner is coming from phi. Okay. Yeah.
Sorry, I might have got lost, but for the time dependence, where we approximated the energy is the rest energy.
Yeah.
The line above.
Mm-hmm. Yeah.
That has the same sign for both phi and pi. I might have missed that one.
Yeah, it looks like there's a typo. It looks like this should be minus, right?
Oh, okay.
Yeah. 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 So this is a typo here on this slide. On slide 24, this should be a minus. Right? Yeah, because here what I've done after this is 0, I pull this minus sign out, right? To get this minus sign, and there's a factor of mc squared coming from the derivative of this guy. Yeah. Okay. Yeah, I'm glazing over some details here, but and so what we have, right? So we can basically decouple, so we can set these chi's to 0, right? And if that's the case, what we really have is just one equation, and it's the equation for phi. And what's left over is this, right? This thing plus the interaction term operating on phi. Right? And you can use an identity that you've probably seen. So when you have a product of your Pauli matrices dotted into a vector times itself, you can rewrite that in terms of the other vector squared and then the cross product, right? But the cross product of a vector with its own is 0, right? So that part goes away. And where did this come from? Wait. PNA. Oh. What's okay. So what I must be doing, and again, you guys check me on this. When I take this cross product, I must be plugging in for my expression phi or pi, right? And then rewrite P in terms of the del operator, right? And so I'll get a cross term in this cross product that looks like del cross B. Is that A? It is? Del cross, no, del cross A is B. Yeah, okay. So that's where this B is coming from, okay? Sorry. Okay, so you use this identity. This is the general form of the identity, and then use a fact. You plug in those two pieces, and you'll get a cross term, like I said, that gives you this piece. And so finally, what we can do is plug that in, right? And we get a term that looks like our kinetic energy term with that substitution, that minimal coupling substitution. Interaction of the spin, right? The spin of a particle with with the magnetic field, and then the electrostatic interaction. And this is an equation that maybe you've seen in undergrad. I don't know. I don't think we touched on it here, but it's called the Pauli equation, and it's basically the equation, the correct equation that you would write down if you were studying a non-relativistic particle in this situation where you have a non-relativistic particle interacting with an electromagnetic field. Maybe you've seen where they've reduced this part or they've squared it out or something like that. But the point is that by taking this approach where we split the Dirac spinner into these two component spinners, and then plugging that in and carrying it out, you get a set of coupled equations, meaning that phi not only depends, it depends on chi, right? Chi, the equations for phi and chi are coupled, right? And so one way you can decouple them is take the non-relativistic limit, what you find is that in that limit, these guys reduce to this, and then you can plug that in, right, to the Dirac equation, and take the limit, and what happens is this piece, you solve for chi, right? Yeah. Okay. Right. Yeah. Sorry, I lost train of thought. Anyways, the important point is that we get the correct non-relativistic equation. So the Dirac equation, at least, so we've seen now that it's manifestly Lorentz invariant, meaning it's good for special relativity. We've seen that it obeys laws of quantum mechanics, or at least it gives us the right probabilistic interpretation. And now finally, we see that when we take the non-relativistic limit, we get the correct equation, right? So it looks like we're in business. Okay. And so what I want to do now is kind of dive deeper into the Lorentz invariance of this guy. So we've seen, it looks like it's Lorentz invariant because it has time and space on equal footing. But what I want to do is try to check that in a more explicit way. Okay. So our goal is to show that the Dirac equation and the continuity equation that you get from the Dirac equation are Lorentz, are covariant or invariant under Lorentz transformation. I can never remember the difference between invariant and covariant, but so to me they're the same. Okay. All right. So what's a Lorentz transformation? So let me remind you. Okay. So a Lorentz transformation is it's a transformation that takes you from one inertial frame, in other words, not a non-accelerating frame, to another inertial frame. Right? And so a lot of times you'll see the notation for these two frames be O and O prime, so I'll use that. So the observers in those frames, if they witness some event, will see it, in different ways. But the important thing is that if you try to use physics in these two frames, you should get the same results. Right? So if you want Lorentz invariant theory, then the results of these experiments should be the same, and so that's what we want to do. We want to check that in one frame, if the Dirac equation holds, then in the prime frame, its Dirac equation should also hold. Okay. And so the Lorentz transformation is kind of the rule that relates these two frames. And typically what you see is a four vector. So just the general, this is the spatial four vector, but a lot of times we just show just a general vector. But so this is a vector saying that, or this is the equation saying that this guy is the Lorentz transform frame, and you get it by applying some matrix operation on your four vector and your unprimed frame. Okay? And so a lot of times, so here I've written the sum explicitly, but you guys all know that whenever you see repeated indices, one up and one down, that means that you're summing over those indices. Okay? So we apply some matrix, we'll call it the Lorentz transformation matrix, onto our four vector. It gives us a new four vector in the primed frame. Okay, and this Lorentz transformation matrix is going to only depend on the velocity and the spatial orientations. Okay, so that means that it's going to depend on the difference in velocities of these two guys, and the orientation, meaning, you know, if this guy's rotating a little bit. So we're not only going to include boosts in our Lorentz transformation, but we're also allowing for rotations of our frames. Okay, we're going to try to be completely general. And so so the basic invariant, the basic thing, the basic scalar that is invariant under a Lorentz transformation is what's called the proper time interval, or sometimes we call I can't remember what is it? Yeah, it's just it's basically like the length of you know, the magnitude. I can't remember the name. Anyway, so you can write this. So this is some small element, right? It's dotted into itself, so it's a scalar, and you can write that down in terms of two four vectors being contracted with the metric tensor. Right? Everybody knows metric tensor. You can write it like this, or you can write it like this. Okay? And because this thing is a scalar, it's preserved under a Lorentz transformation. The line element, that's what I was trying to think of. Okay. All right, so again, so this guy A is going to be our Lorentz transformation matrix, right? And G mu nu is the metric tensor. Okay? And you can show that our first two expressions, this guy, the fact this transformation, and this line element equation, you can show that if I dot two of these Lorentz transformation matrices into each other, right? So I'm summing over mu here. It gives me a delta function, basically identity matrix. Okay, so remember, keep in mind that these guys are 4x4 matrices. All right, so there's two kinds of general Lorentz transformations. One's proper. That means the determinant of this thing is +1. And so these types of transformations include boosts and rotations. And then there are improper transformations that mean, explicitly it means that the determinant of this guy is -1, right? And so these are kind of our weird discrete transformations like parity or spatial inversion and time reversal, okay? But what we'll be focused on is this guy, okay? Right, so what we want to do is try to find a transformation law that relates the two observed systems, but we're going to be working with the Dirac equation. So that's equivalent to saying, okay, I want some rules, some transformation law that relates the wave function that, you know, the person in the frame O observes, right? Or doesn't really observe the wave function, but this is the wave function in the O frame. This is the wave function in the O prime frame. Right? So what we want to do is try to find the relationship between those two guys. So what we want to do is develop a rule so that, you know, if we solve the Dirac equation in the unprimed frame, we can apply that Lorentz transformation to the wave function and get back the wave function in the prime frame, the correct wave function, right? So we'll have a way of going back and forth between these two frames. Right? And what we should see is that, you know, the form of the Dirac equation is the same in the two frames. Yeah, that's right. Okay. All right, so what we're going to do is introduce some new notation, okay? And what it does is it makes the Lorentz invariance or covariance a little more explicit, okay, or more manifest is what they say a lot of times, okay? And so so you're asking yourself, well, we've already done that, right? But the thing that we haven't really worked on or worked with are the alpha and beta matrices, right? So what I want to try to do is unify those guys into one quantity, okay? It's going to look like a four vector, okay? But remember that it's not a four vector. These are matrices, okay? It's an important point, and it seems kind of trivial right now, but you'll forget as you're going along, okay? So the way we want to do this is we want to first take our Dirac equation, all right? So this is what take our Dirac equation, and we're going to multiply it from the left by beta divided by c. So the matrix beta divided by c, okay? And now it gets confusing because we're talking about special relativity, and we always have the beta, which is b over c. Right? This is beta, the matrix, right? The matrix, okay? So if I multiply beta, right, and so I get the beta term in front of this time derivative, I get the beta in front of these guys, and then here I get beta squared, right? But you remember that all those Dirac matrices, the alphas and the betas, when you square them, they give you the identity matrix. Right, so I can replace that with just one, or the identity matrix. Okay, and then I define some new matrices. Okay, so this guy beta here, I'm going to call gamma 0. Okay, and then the combinations coming from this product, so beta times alpha I, beta times alpha 2, and beta times alpha 3, I'm going to call those guys gamma I. Sorry. Okay, and so I can construct these new matrices. So this one's just the same beta, but here I have to multiply beta times alpha I to get their respective gamma I. The important point is, though, that when you do this, you can write this in kind of a four vector notation, right? So if I bring everything together, and I remember that the covariant form of the derivative has an opposite sign of what we're used to, right? We can rewrite this as gamma mu being dotted into our del mu. All right, remember, normally when you dot two four vectors, there's a minus sign in the last three component parts. But here, del mu comes with a minus sign. Everybody remember that? So remember, when we write mu downstairs, this is the same thing as du. So I'm leaving out some constant, and that's minus. Okay, so that's how I get the sign here. Anyway, so we can combine that into gamma mu dotted into del mu. Okay, so this is where it looks a little confusing, right? Because gamma mu, so it looks like it's a product of two four vectors, right? But you have to keep in mind that these guys are not four vectors; they're matrices. Okay, so on the surface, it looks like a four vector, a product of four vectors, right? A dot product. And so you would say, okay, this is a scalar, right? This is a scalar, so it must be Lorentz invariant, right? But it's not necessarily true because this guy is not a normal four vector. It just looks like a four vector. Right? And a lot of times what you'll see is you can pretty this up even more by introducing something that Feynman invented, which is called the Feynman slash. Right? So anytime you see a vector being dotted into a gamma matrix, right? So like this, you can write it as a slash. Okay? So it's just a cute little notation, but it means just, like I said, it just means that this vector a mu is being dotted into the gamma matrices. Okay? And so when you do that, you can get to the Dirac equation in this form. Right? And so now, and typically what we do in high energy physics or in relativistic physics is most of the time we set C and H bar to 1. That's what you have before, right? These are called natural units. Even though it doesn't seem very natural to set stuff to 1, but anyways, so you would have I del slash minus M operating on the side, right? And that kind of includes all that stuff that we wrote out in the big long Dirac equation. Okay, you can write it in this nice compact form. Okay, and then finally, what you can do is, so we have these new matrices that are built out of alphas and betas, right? So what you do is you go back, you try to compute you want to find out how these guys play together. Do they commute or do they anti-commute? Right, and so you can go and you can compute, say, that anti-commutator, and you use the relations for alphas and betas. And what you find is that this guy, the anti-commutation relation looks like this. So gamma mu gamma nu, you get g mu nu. So these are the components of the metric tensor. Okay, these are the components of the metric tensor. And what is usually implied, and it's hardly ever written, is that there's a 4x4 identity matrix here. Okay, so keep that in mind. I don't think I have you do any of proving things like this, but keep in mind if you go to a higher level course, always remember that there's a hidden 4x4 matrix here. All right, so these are components of the metric tensor. This is the 4x4. Okay. Okay. And you can also show, using the identities of alphas and betas, that these guys are anti-Hermitian, right? Meaning that when I take gamma dagger, I get minus gamma, right? Gamma I squared is -1, right? So it's not 1 anymore, it's -1 because it's anti-Hermitian. And gamma 0, but gamma 0 is Hermitian, right? It's because gamma 0 corresponds to beta. And so what we end up with is in the vowel representation, you can compute these matrices and you find that gamma I basically looks exactly like alpha I. I think there's a flipping sign here maybe. And gamma 0 is just beta, so it still has this form. Okay? So I'm going to stop there. But basically what we've done so far is just kind of massage the Dirac equation and get it in a form that's a little easier to deal with. Okay, and it's the form that you'll see. You never see people working with alpha and beta matrices. You always see people working with the gamma matrices. Okay, because it's easy when you write down a theory. If you write down some extension of this theory, like say you add some piece to it, you want to be able to show that it's Lorentz invariant. And we're going to see that even though these are matrices, anytime you see this combination, that is Lorentz invariant. Okay, we'll prove that next time. But so everybody works with the gamma matrices. Okay, so next time we'll do the proof of covariance using this form of the Dirac equation. Okay, all right. I'll see you Friday. Okay, just remember that so I'll send out an email just to remind everybody. Any questions on anything? No? Okay, so go. I mean, I strongly encourage you. This is something that is hard to, you might, it might look like it makes sense. Looks like it makes sense, as I'm presenting, or maybe it doesn't. But work through it. It's not hard, and you'll get a good feel of the Dirac equation doing it. Okay. All right. See you Friday.